is finite element methods and geometric integration. I've very much forced the word geometric into the title, and I'm going to tell you a little bit in my motivation what I mean by this. And then gradually I'll move on to actually what I want to talk about, which is derivation of numerical schemes that are, hello, derivation of numerical schemes that are satisfy certain physical quantities that you would want to force into them. Okay, so on to the motivation. So this is deliberately simple. So I'll tell you a little bit about geometric integration. So it's basically a term used to describe a class of numerical methods that exactly preserves certain properties of differential equations. So in the simplest instance, you might be talking about energy-preserving schemes, or symplectic schemes, or even those that preserve some crazy Lie symmetries or something like this. What I'm going to focus on is energy-preserving schemes, and I'll mention briefly how this relates to symplectic schemes for the ODE case, just in the beginning. So I want to start with ODEs. Nice and simple. So I'm going to look at this class of ODEs here. So this is a Hamiltonian system of ODEs. So H here is the Hamiltonian, U is my solution, which is it's a two-dimensional, it's a 2D system of ODEs, and J here is some skew-symmetric matrix. Okay, and the simplest example of this that I could think of that was non-trivial is the pendulum problem. So let's have a look at this. So in this case, my Hamiltonian is described by this function here, and the system, we all know, is written in this form here. So you have two unknowns, P and Q, and this is the pendulum problem. Okay. And for Hamiltonian systems, there's some very nice properties. I wouldn't be able to derive numerical schemes with very nice properties if the underlying ODE system didn't have very nice properties. So let's look at these. So they tend to be derived from physical phenomena. So the pendulum problem describes the motion of a pendulum, undamped, and this means that certain quantities are conserved. So in this case, the Hamiltonian itself, which represents the total physical energy of the problem, is conserved in time. And what I wanted to show you was how do just bog standard, the first numerical discretizations you would ever think of, how do these respect this law here? So how is the Hamiltonian conserved under certain standard discretizations? So I show this to my undergraduates when I give them their first numerical analysis lecture. This is kind of fun. So if I take my pendulum problem and I just throw a forward Euler discretization around it, standard forward Euler, explicit, first order, nice and simple, first thing you would think of doing, what happens to the solution? Well, if I run the video, whoops, if I run the video, what you can see is a very weird and wonderful behavior. So I've deliberately chosen parameters to exacerbate the funny behavior. But what happens is really weird. It's not what you expect. So you've got an undamped pendulum, so you expect it to just swing from side to side, but it doesn't. It actually seems to want to try to go to the unstable equilibrium. And why is that? Well, there we go. If you look at the how this Hamiltonian function evolves over time, you can see this really horrible behavior. So I already told you that for the problem itself, the Hamiltonian is conserved over time, right? So what I would like is a numerical scheme that says, well, my Hamiltonian deviation over time is 0. But forward Euler doesn't do this. Forward Euler is, we know it's an unstable method, so it actually essentially over time adds in energy into the system. Numerically, so this is a numerical artifact. Okay. What about other discretizations? So, okay, forward Euler didn't work very well. Let's try backward Euler. Backward Euler suddenly is an implicit scheme. It's still first order. So what does this do? Well, I can play the video again and oh, it's a bit more physically meaningful, right? The pendulum is at least going to what we think of physically as the stable equilibria, but the model itself didn't have any damping in it. So I don't really want this to happen. And again, if I look at the deviation in the Hamiltonian over time, you see it just goes away very, very quickly. And this is because the method is a dissipative method, right? Backward-Euler introduces artificial or numerical dissipation. And this is why we call it, well, a reason why we call it a stable method. So physically, it does nice things, because physically, that's what a pendulum should do. But in the mathematical model I was using, there was no damping, so I don't actually want that to happen. If I wanted that to happen, I would have included damping in the model in the first place. Okay. So then I think a little bit harder. I say, okay, well, I tried forward-Euler, which was one end of my scale of my theta methods. I tried backward-Euler, which is the other end of the scale of my theta methods. What if I go slap bang in the middle? If I go slap bang in the middle, I end up with a Crank-Nicolson discretization. So this is what a Crank-Nicolson discretization looks like. Still implicit, now it's order 2, so it's a bit higher order. It's a bit better in terms of accuracy of the method as you refine the temporal partition. And it does a good job. You've got your little pendulum. It goes back and forth as you think it should. It doesn't go crazy. It doesn't go to this sort of unstable equilibrium. It doesn't damp away to nothing. And this is why. So this is the deviation in the Hamiltonian again. Take note of the scale. So it looks kind of oscillatory and horrible, but the scale is now 10 to the minus 3. So you have very small oscillations. Importantly, they're bounded in a fixed region, right? So in long time, you can actually show this in long time. The oscillations will continue bounded in this region. So you don't damp away. You don't artificially add energy into the system. So this is, I claim, a good method for this.
Does it scale the same way as your order?
That's a very good question. Yeah, so I played in my head as to whether or not to include this, and now you asked the question, I'm going to show you. So in the background, he says he has MATLAB open. He says, with the, no he doesn't. Application not responding. Fine, we're going to ignore that and go back to that. Yes. So for example, I could do this with Hoyne's method, so second order explicit method, and you will still get artificial or numerical energy added into the system in the same way you did with forward-Euler, not quite to the same extent. Asymptotically, as you send your discretization parameter to 0, you have to be doing the right thing. So right, but for fixed time step, you're still doing the wrong thing. You're still either adding in energy or you're removing energy. So if you looked at BDF formulae, for example, you'd be damping still, right?
Well, the question though is, if your method is order delta t to the n, how does the deviation in the Hamiltonian scale?
It has to go to.
Well, sure,
yes. So higher order methods will do better,
okay.
For sure. Higher order methods will do better. That's what I was going to show you, but my MATLAB doesn't work. Never try and run code in a live environment. Okay. So I had conservation of this quantity up to order 10 to the minus 3 or something. Can I do any better? Can I conserve this quantity exactly? And the answer is yes. There are a class of numerical methods that allow you to do this. They're called discrete gradient methods. They're not Runge-Kutta methods, though, funnily enough. You can't write them as Runge-Kutta methods, but they are kind of close to Runge-Kutta methods. So here's an example of one. Here's the simplest one. What you do is you replace derivatives. So this is a Hamiltonian problem, so there are essentially derivatives here. You replace derivatives by difference quotients. And if you look at this difference quotient, you'll see it's a good approximation of sine at qm plus half. If you look at this and you use Taylor's theorem and expand about, you see this. So it is a high order perturbation of Crank-Nicholson method. It's Crank-Nicholson method tweaked a little bit to do what we want. So I can show you another video. I don't know what it looks like. That it's funny. This is the method again. More or less in the I norm, you won't see any difference to how this behaves compared to Crank-Nicholson method. But if you look at the deviation in the Hamiltonian, and again check the order, this is now 10 to the minus 15, which is machine precision in the simulation that I ran, or at least the precision of the Newton solver that I was using to solve the problem. So here the Hamiltonian is conserved up to machine precision. This is what we like. So this is I claim a reasonable thing to do. So yeah, so this is what I said before. The method itself is just a high order perturbation of a Crank-Nicholson method. It is of the same order of accuracy as Crank-Nicholson, but slightly different. The perturbation doesn't hurt you in terms of asymptotic convergence. Okay. So a related geometric quantity is called symplecticity, and there are various schools of thought in the numerical analysis community as to which is better, symplecticity, energy conserving. Usually symplecticity wins out. I'm not going to comment on that, but we'll see what it is first. So you can define it in some terminology. Yes?
Sorry, is there a reason why you only take the derivative or the approximation of the derivative for the cosine and not of the other term?
Because this term is quadratic.
Okay, yeah.
Right. So yeah. So if your Hamiltonian, so I said I was looking at the pendulum problem as the sort of easiest non-trivial example I could think of.
Yeah.
If I looked, for example, at the harmonic oscillator, yeah, the harmonic oscillator, my Hamiltonian is quadratic. For quadratic Hamiltonian, you can do some very nice things. I mean, this is basically a linear problem, then, right? You can solve it exactly. But your numerical schemes turn out, Crank-Nicholson will be energy conserving then, in this case. So for quadratic integrals, Crank-Nicholson does very, very well. So this is why there's no difference quotient here, is exactly because this term here is linear, and difference quotients do very well then, yeah? But so this is, the reason the difference quotient comes in is because of this nonlinearity that is worse than quadratic. That's the idea.
Thank you.
No problem. Yeah, so back to symplecticity. So this is just some geometric quantity, actually a very important geometric quantity, that can be written in terms of differential forms or the flow of the flow map of the Hamiltonian system. And another good reason to go for a two-dimensional Hamiltonian is that you can give it a very nice intuitive definition. So for the pendulum problem here, it's actually equivalent, this property symplecticity is equivalent to area conservation in phase space. What do I mean? So I mean, if you draw phase space, so this is the phase portrait of the pendulum problem, and what I've done, or I didn't do it, the student did it, what I did is superimposed a load of initial conditions in black, it's the Batman symbol, and I ran it for a certain amount of time and saw what happened under the flow of the solution. Yeah. So what you can see is the area, well, you can't see, but in the eyeball norm, the area of the Batman symbol in black is the same as the area in blue. Yeah. So over time, my blob of initial conditions, yeah, the area is conserved. So heuristically, this is what symplecticity means. There are some much more complicated definitions that I could give you, but I won't. And what we're interested in again is how do our numerical schemes behave? So if I look at the phase space, my numerical phase space now, for forward Euler, how does this affect my blob of initial conditions? So for forward Euler, what you can see is it stretches and smears. And the reason for that is well, partially because of this addition of energy into the system. So in the eyeball norm, probably you can make out that this is actually a larger area than Batman. Okay. And for backward Euler, what would you expect? You would expect it to dissipate, right? So the area of the blob of initial conditions decreases. Okay. And the only good one seems to be the Crank-Nicolson method, of the three that I'm testing anyway. And this conserves the area, and in the I norm anyway. But moreover, you can prove this. So neither forward or backward Euler are symplectic. They don't conserve the area in phase space, but Crank-Nicolson is. And this is a symplectic scheme, and you can prove this is a symplectic scheme. And this was done a fair amount of time ago by Sancerna, maybe in the 80s, I think. Okay, so this is just a little summary of what we've got in terms of the two geometric properties of these little integrators that I wanted to look at. So forward and backward Euler, both order 1, neither energy conserving and neither symplectic. But as you pointed out, you could go to order 2 explicit and order 2 implicit methods, and you would find, so for example, Hoyne's method, you would find the same property, and BDF2, you would find the same property here. Crank-Nicolson is symplectic, but not energy conserving. And the discrete gradient method I mentioned, I didn't show you the phase portrait because in the I norm you can't tell the difference, but you can show that this is not symplectic. So quite a natural question comes from this. Can you have both? The answer is no. You can't have both. You can't be symplectic and energy conserving unless you're in the very special case of a quadratic Hamiltonian. Then you can. So, so there's this famous theorem by Goe and Marsden. So they say, no, you can't do both at the same time unless the problem is a trivial problem, like this quadratic harmonic oscillator problem. Okay. Yeah, so the title was Finite Element Methods and Geometric Integration, so I thought I'd briefly put a little bit on finite element time discretizations. I'm not going to go into this later on, but this is roughly what we're doing. So if you rewrite your Hamiltonian system just in this simple form, the idea of a finite element method is a variational problem, is that you multiply by some test function, and you integrate over the domain you're interested in, the temporal domain in this case, and you look for your solution in this strong form. Okay. And then to discretize this, you do more or less a similar thing. You divide your temporal domain into some partition. You specify intervals and mesh sizes, and you say, okay, where am I going to look for my solution? Maybe it's a good idea to look in continuous piecewise continuous polynomials of degree q, say, linears, quadratics, whatever you like, and then you restrict the strong form of your problem onto this polynomial space. Okay, so that's basically the idea of the finite element method in time. Right, so, and what can you do? I mean, the finite element method is a well-studied thing, and you can show lots of lovely properties. This has all been done in the 60s and 70s. So you can show, for example, pointwise error control of your finite element solution to the solution of the ODE up to some order of accuracy, dependent on the regularity of the solution of the ODE. You can do a posteriori analysis. This is where you try and control the error by things that you know. So I know it's my finite element solution, so I can quantify my error just in terms of the solution itself, the discrete solution itself. That's kind of neat. But what about if I tried to use it as a geometric integrator? How does it behave? What does it do? Does it conserve energy? Is it symplectic? Well, I'll summarize the points. I won't go into the details. It does conserve something close to energy. It conserves a discrete Hamiltonian that is not too far away. And what is kind of interesting is if you pick specific quadrature points, so when you're doing this variational formulation, you're integrating something, so you're never going to integrate things exactly, so you use a quadrature to approximate this. And if you pick specific ones, Gauss quadratures in this case, you arrive at a symplectic numerical method, which is quite fun. And you can do similar things for Petrov-Galerkin, discontinuous Galerkin in time, but I won't go into this. Instead, I'll start talking about what I really want to talk about, which is how do you use numerical methods in more complicated problems. So I showed you the ODE case. I showed you the Hamiltonian case. We know what's happening in the Hamiltonian case, and geometric integration is pretty well known in the ODE case. In the PDE case, it's not it's not so well studied. So I'm going to tell you a little bit about the Navier-Stokes-Korteweg system. This is quite pixelated. So what I'm interested in is a convection-dominated flow, single substance, but that may have two phases. So for example, if you look here, you have liquid and vapor phases. I care about the case when we're compressible and isothermal, and I want to derive a model that includes phase transitions. This is the point my bubbles need to be resolved, and I want my bubbles to allow for topological change. And from the applications point of view, you can say this comes up in fuel injection and water meter ship's propeller. Okay, and the model I claim is a good model for this. I'm not a modeler, but the model we chose to study is a Navier-Stokes-Korteweg system, and this is a diffuse interface class of model. Okay, so what we do is that the reason we do this is because we have one set of PDEs that we solve on the entire domain, and the position of the interface, this thing here, is hard encoded into the system itself. So I don't have to do things like track the interface and play around with this. I don't have to worry about sort of bulk surface coupled PDEs. It's simple for me to deal with. I'm going to look at the case where this interfacial layer is thin, but not the sharp interface limit. Okay, and this is the system that I claim is a reasonable model for this. So this is Navier-Stokes-Korteweg. So here you see the Navier-Stokes equations. Here you see a little Korteweg term kicking up. So this is a third order term, nonlinear. The density is rho, the velocity is v. Mu here is my diffusion parameter, and gamma is my capillarity coefficient. So gamma, it turns out, tells us how thick the interfacial layer is at the end of the day. And we deal with the case where we've got these boundary conditions. So the velocity vanishes and the normal derivative of the density goes away. Okay. And you saw, sorry, I missed the pressure function. So P here is a pressure function, which is linked to this double well potential, W. So I'm going to say W is a double well potential, and P is my pressure function. So it might look something like this. It depends on the physical system that you're looking at. But there's this Helmholtz type relation between the two. Okay. And what you can show about the system is if you've got smooth solutions to it, say strong solutions to the PDE, then you have this really nice energy dissipation equality, I call it. So it tells you, so this quantity here is the associated energy to the system, and it decays. So this term has sign, this is a positive, sorry, this is positive, so the whole thing is negative, which means if mu is non-zero, my energy decreases over time. And this is a reasonable thing to build into a physical model. Okay, so, right, so consequences of this identity are that the gradient term, so here's the energy written again, so the gradient term, this term, gives rise to my diffuse interface, so gamma here dictates the width of my interface. Because I have this decay in energy, I'm thermodynamically consistent, and well, steady states of the system minimize the energy function. And because of this, we satisfy some Euler-Lagrange equations. And I want you to pay particular attention to this one. So the velocity is 0 in the steady state. This is a reasonable thing to have in any fluid simulation. Yeah, and lambda here is a Lagrange multiplier. Okay. So let's throw some standard schemes around it again. Let's do what we did in the ODE case. If I put a finite volume scheme or a DG scheme with normal flux choices for conservation laws, Enquist-Osher or Lax-Friedrich, you have some artifacts coming in the same way we saw that forward Euler for the pendulum made you do weird and wonderful things and backward Euler damped you. Standard schemes do funny things here. Parasitic currents and non-monotonic energy. So let me tell you what they are with a video. Okay, so this is in German, okay. This is a German video. So what you're looking at here is, here is the density and this is the velocity. You start with, let it go back to the beginning again. Oh, it very quickly goes away. You start with a step function for the density and the velocity starts at 0. So what the system wants to do is develop this diffuse interface between two phases, this being one phase, I don't use the pointer, and this being the other phase. So it wants to develop this diffuse interface, and it does that, and you get some oscillations up here. But what I want you to pay attention to is as the video plays, this velocity here, this velocity that develops here, doesn't go away. So if you remember the Euler-Lagrange equations from a couple of slides ago, I want the velocity to go away in the steady state. That's how things should be, but it doesn't go away. What's happening is that the fluid is pushing in at the interface on both sides of the interface. So here and here, we're pushing in this direction. And the amount you're pushing by cancels out, but it's non-zero, and it's not physically doing what I want it to do. So I've designed my model that satisfy so that steady states satisfy these criteria. The velocity disappears. My numerical scheme doesn't respect it. Same thing happens in 2D. So here again, this is just the density now, and the velocity is overlaid with a glyph plot. So the arrows represent the velocity. So you have blue representing low density, orange high density. So initially you start off with a square bubble, and square bubbles aren't very energetically favorable, so it tries to go to a circular bubble, and it does that very nicely. But what you can see is on the interface, the diffuse interface, you have a non-zero velocity. Again, the forcing of the force induced by the velocity balances out on average, so your bubble doesn't really go anywhere, but it's still non-zero. Interestingly, it always seems to be the case that the velocity goes from low density to high density. So if I showed you the video again, the velocity always wants to go from low density areas into high density areas. Okay. It's the same in the 2D case. Okay. And this is the other artifact, which is non-monotonic energy. So you can see, so here n represents the number of degrees of freedom. This is for the one-dimensional simulation that I showed you. So So it's the number of nodes in my one-dimensional simulation. You see the energy is increasing here. The energy is flopping around here. This shouldn't be the case. I've specifically designed my model so that I'm thermodynamically consistent. I specifically designed it so I have this energy dissipation. My numerics don't satisfy this. Okay, so yeah. So for fixed H, my numerical schemes are actually losing their nonlinear stability. They have no nonlinear stability, and they are not thermodynamically consistent. So how do people deal with this? Well, people have done some work on this problem, and what they do is they, very roughly what they do is they add in tons and tons of artificial viscosity, which doesn't exist itself in the model. It's numerical. So they add in a ton of numerical viscosity to try and overcome things like this. Which, okay, that works, but this viscosity is non-physical. Why did you not just derive a more viscous model? It's a numerical thing, and it's a typical numerical trick to get over this is to add a load of diffusion into the scheme itself. So what I want to look at is can I design schemes that satisfy these nice properties of the model? Yeah, so I want to construct a numerical scheme devoid of these artifacts without having to add in tons and tons of artificial diffusion. Okay, and then this is something that I did with Jan and Babis and me, and it was published in MathComp last year. So what we said is, well, how are we going to do this? Well, we want to mimic how we did this at the continuous level. So I want to go back to the model, the PDE model, and I want to see how this was, how did I actually prove my energy dissipation equality? I'm going to sketch this for you. So I've got my Navier-Stokes-Korteweg system, which I've labeled. And what I do, very roughly, is I test the first equation with this quantity here. It's actually the first variation of the energy. But, I test the second equation with the velocity. I add the two up. I play around. I use Stokes' theorem. I use the boundary condition. I make things disappear. And I'm done. So if I was trying to do this in a finite element context, what difficulty would I have in doing this? Which one of these steps can I actually not mimic at the discrete level? It's the first one. So I can't test by this quantity here because it's a nonlinear quantity. Right? So for example, here I have the square of the velocity. If the velocity is a piecewise linear continuous function, how am I going to test with the square of the velocity? It doesn't live in the right space. It's not in the finite element space, so I can't test with it, and I can't do what I like to do. So how do we get around this? Well, it's a very simple idea. Reformulate the system. Reformulate the system so that this exists as a function that I can test with. So this is all I do. I take the original Navier-Stokes-Korteweg system and I rewrite it in a mixed form. I introduce an auxiliary variable, Tor. And this Tor, if I go back a slide, this Tor is exactly this term. Yeah? So I have my Tor now. So I have my quantity. Eventually, when I discretize this thing, probably it lives in the right space and probably I can do nice things. Yeah, okay, I highlighted it there too. But this is the trick. It's quite a simple trick, but it's actually the trick. Okay. I'm not going to go into too much detail, but the numerical scheme that I want to use is a DG scheme. So it's a discontinuous Galerkin scheme. So roughly, this is some of the notation you may need. So I take my domain and I triangulate it in some fashion. I let V be the space of piecewise polynomials, not necessarily continuous. This parenthesis here, it represents the average of the function over the edges in my triangulation, and these guys are jumps. Okay, it's okay, they're something. So what I do is I take my system, my mixed system that I just rewrote, and I write it in strong form. Okay, I write it in strong form over my domain that I'm interested in, my square, say. And then on my triangulation, I introduce flux terms over the edges. So this curly E here is the set of all edges in my triangulation. So these are just flux terms going from one triangle to another. There we go. And what I try to do is to construct certain criteria where these flux choices do the right thing, give me what I want. So this is what we can prove, basically, is that if I want, if I choose my flux functions in specific ways, okay, looks horrible, but it's generic conditions that if I can choose my flux functions in such a way, then I will have conservation of mass, which is a necessity in these problems, and dissipation of energy. Okay, so I have this discrete energy dissipation. So this here, this is just some signed discretization of the Laplacian in this case. Right. So all this says is that in this mixed form, I can come up with conditions on my fluxes, on my discretization, that allow me to get what I want. Get rid of this non-monotonic energy. So this is now monotonic, guaranteed. Okay, and I flash up generic conditions, but then you ask me, can you actually find some that satisfy it? The answer is yes, you can. You can find fluxes that satisfy this, and this is what this scheme is here. So it is what it is. It looks horrible. It's okay. So the point is that if you have no diffusion in your model, which isn't necessarily a good idea, but let's say you do, if you have no diffusion in your model, the energy identity from the previous slide, this guy, tells me that energy is conserved. Yeah? So in the same way we designed a numerical scheme for the pendulum problem, the pendulum problem itself isn't a good model without diffusion, I mean, but we can design schemes that are energy conservative. This is semi-discrete, by the way. I haven't discretized in time yet. Yeah, and this is an example of a bilinear form that satisfies conditions that I need. Fine. So if you discretize in time, what am I going to do? I'm going to use what I know already from the ODE case. So I already know how to deal with massive systems of ODEs that are energy conservative. I know how to deal with Hamiltonian ODEs, for example. So in time, what do? I take my mixed formulation, again, this is what this is, and I discretize with one of these energy conservative time discretizations. So what you can see are these funky difference quotients flying around again, in the same way that we had them in the Hamiltonian case. And actually that's what this is. This is exactly a Crank-Nicholson discretization, with the exception of these red quantities, which are slight perturbations, allowing me to have this lovely property, which says, in time discrete case, I am energy conservative up to this point, and then this bit is signed and dissipates energy. Okay? So, and to do the fully discrete case, you tie the two together in a natural way. So what does it tell me? It tells me that, yes, if you are smart in how you design your numerical scheme, you can design schemes that are that respect the laws of physics inbuilt into your problem. Okay. Proof is in the pudding. Can I actually show you some results? So I can construct traveling wave solutions of the Navier-Stokes-Korteweg system. I'm not going to show you how, but I can. And I can benchmark. I can benchmark my numerical scheme against the exact solution and see what's happening. And what I do is I look at the error in density and the error in velocity, in this Bochner space here, L infinity L2. I measure it and I see how it behaves as I increase the number of nodes in my discretization. And what it tells me, well, you can see the numbers going down. What it tells me is that the scheme converges, and it actually converges with optimal rate, the correct rate. So here's a little one-dimensional simulation of the Euler-Korteweg system. So this is without diffusion. So I told you it wasn't a good idea physically. I think you can see that now. So what happens is, so I start with the same initial condition that I did before, which was just this step function. And come on, there we go. You see these dispersive waves coming out. So this is exactly because the Korteweg term is dominating, so I have dispersion entering in, and I have these oscillatory waves that will never go away because I don't dissipate at all, because my diffusion is 0. So from a modeling point of view, it's not a good idea. But it makes for a really good numerical test. Ta-da! So what this is a plot of the energy and the mass for that simulation. So the energy is on the left, the scale for the energy is on the left, scale for the mass is on the right, energy is in red, mass is in blue, mass is conserved, energy is conserved, which is really nice, because that's exactly what I wanted. Okay, can I remove the numerical artifacts from the case I showed you right at the beginning? So again, you can actually see the initial condition here. Very good. So again, I start with this step function for the density, and what you see, it's the same simulation that I ran before. This does the same thing. Importantly, the velocity, if you look here and here, this is where the interface is, it's going to 0. And in the limit, it does go to 0. So let's let it go through one more time. There we go. Wibbly wobblies, and then goes to 0. So it removes, so having a scheme that preserves this energy monotonicity seems to remove the parasitic currents as well. And it's not just a 1D phenomenon. I showed you where it broke in 2D. Oh, let me show you this first. So here is the monotonic energy decrease for the simulation. And I'm conserving mass, which is wonderful. So it was a 2D simulation as well. So here's my initial conditions. Sorry about the funny picture. This is Pac-Man, and Pac-Man's going to eat the little bubbles. So off he goes. So again, the velocity field is on the right and is given by arrows. This is the density. So you can see the interface here, and you can see that energetically it's more favorable to be one bubble in the middle. So all the bubbles merge together, and as they go, you'll see a spike in velocity. Blob, 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 blob. Very good. Very good. And so you see things are still moving around, but gradually the velocity field goes to 0 everywhere. So there's no spike where the interface is, which is nice. Okay. So Navier-Stokes-Korteweg model, I mean, it is a nice model. Some people would argue that it is a bit simple. So now I'll show you something a bit worse, a lot worse. So this is called a quasi-incompressible model, and what we're interested in here is where I have two incompressible fluids, for example, water and oil, and how they interplay. These can have different densities, and this is what I mean by quasi-incompressible. I care about surface tension and mass flux across the interface. Again, I want to use a diffuse interface model just because I like that. And this is what the model has come up with. Gross. So let me guide you through it a little bit. So it's a Navier-Stokes-Korteweg, Alan-Kahn-Hilliard type model. Lovely. So here I've tried to highlight little bits of it. So here, these terms in red, so this mu here is like a chemical potential. Yeah. So this is acting a little bit like an Alan-Kahn type term. Yeah. This one here, there's an extra Laplacian here hitting this chemical potential. So you see a Laplacian squared. So this guy acts a bit like a Kahn-Hilliard term. There's my Korteweg term flying around again. This is the same. This has the same effect as in the Navier-Stokes-Korteweg term. This is the term that governs the interface, the behavior of the interface. So now I have a full Navier-Stokes tensor here. So instead of the Laplacian of the velocity, it's the full Navier-Stokes tensor. It's a bit worse, it's a lot worse. And I have this funny incompressibility condition that is not incompressibility. Yeah. So it looks very complicated, but you can prove, I already said that, you can prove that in a similar fashion, you can prove that if you have smooth solutions, you have this very nice energy dissipation again. So you can see the square and the square, and this is also signed. So everything is signed, so this term will, in general, go down or be zero. And this is the energy. It has a very similar form to the Navier-Stokes-Korteweg. So you can do the same tricks. You can split into a mixed system just to make it look even worse. And then you can discretize this directly. So, lovely, right? So it's horrible, but you can write it down. You can write it down, and more importantly, you can implement it. And it satisfies nice properties. So in that, there is a discrete, excuse me, there is a discrete energy identity. Yeah, so energy is conserved over the time steps, that's what this means, and dissipated at this rate here. So this, or one of them is a coercive discretization of the Laplacian, and one of them is a coercive discretization of the Navier-Stokes term that arises. Okay, so I can quickly show you some numerics. So, yeah, so believe it or not, I can construct an exact solution to that problem. Same trick, just assume your solution is a kind of traveling wave, and you can do the same thing, so I can benchmark it again. I can check that my code is doing the right thing. So I look at my 3 variables that are important, and I see that the errors are decreasing at a rate that is reasonable. This one is high, this one is low. I'll tell you why this one is low in a minute. And again, for a higher order discretization, this converges better. Okay, so experimentally, this is what I found. I can't prove this. I have no hope of ever doing any error analysis on that kind of problem. It's not possible, I don't think, unless you're Superman. Oh. So this is what I found. The errors behave sort of optimally or suboptimally depending on whether or not my polynomial degree was even or odd. And I've seen this behavior before in conservation laws. So it's not undocumented, but yeah. And here the lambda, which was the Lagrange multiplier again, doesn't really have any. So the scheme doesn't really give you any help with dealing with this guy, because my scheme is only designed to be energy consistent, to have this energy dissipation identity. Okay, so, I can see the initial conditions sort of again. So I'm going to run a simulation again, just to show you that the scheme does something reasonable. So what I do is I take an initial condition that is a random perturbation of 0. So it's a very small random perturbation of 0. And what happens is what you kind of expect if you've seen problems like this one before. So some wiggles and wobbles, and yeah, you get a distinct separation of the fluids, and gradually they sort of, it's energetically favorable to have one interface. So if I ran it, or if I ran this video for long enough time, you would eventually have something like this, with one interface in the middle. But I won't let it go that long. No, I cut it before it got too long. Yeah. And a similar plot as in the Navier-Stokes-Korteweg case, you look at the mass over time and you look at the energy over time, and you can see energy is monotonically decreasing. And actually, each of the blobs is where the jumps happen. So there's one, there's two. Where's the next one coming? There, maybe? No, there. Here comes the third. There. There we go. So that's each of the massive energy decreases is when you form bigger droplets. And the 2D case, so sorry about the initial condition quality. So this is a big bubble, and then I've got smaller bubbles again. I didn't do it with Pac-Man this time. Oops. There. So again, it's more energetically favorable to have one bubble with an interface. It likes being at the boundary, so you can see lots of fun things happening. And I don't know, then there's static, and this guy's eventually going to blob over.
What are your boundary conditions here?
So my boundary conditions, the velocity, there's natural boundary conditions on the density and zero boundary conditions on the velocity, and there's another one off the top of my head, I can't remember. There we go. Oh, what does that physically mean? There you are. So, whoops. Oh, I pushed the wrong button. Where's it gone? There. So this is the other one. This relates to the chemical potential and other things. It's essentially the natural boundary condition for the problem. You can think of it like that. Okay. Disgusting. Where did I get to? Oh yeah, and yeah. Again, a similar plot for the two-dimensional case. You see this monotonic energy decrease. There's no increase in energy, and mass is always conserved. So yeah. I mean, the model's kind of neat because the model allows you to go into a rotating coordinate system without actually adding much. So it's invariant. So if I wanted to do numerics in a spinning frame, I can do that quite simply by just adding a couple of extra terms into my model, here and here, accounting for the Coriolis and centrifugal forces. So that's kind of fun. So I thought that was a neat idea. So I went and redid all the analysis again, and then all of the numerical analysis again. It turned out wasn't so hard. And then I implemented it just by adding a couple of terms into the implementation. You end up with a different energy functional, which suddenly accounts for these terms here. And yeah, you can do the same thing again. And you get an equivalent identity that says, brilliant, I have a numerical scheme, it has some kind of discrete equivalent to the continuous energy. And yeah, so what this is now is an initial condition with a blob in the middle that is slightly off center, and it's in a rotating coordinate system, so it's spinning, essentially. Think of it in a centrifuge or something. And it goes, whee. It goes. And it breaks up. It's kind of fun. It blobs off. And because of surface tension, it doesn't try to travel around too much.
So is the blue higher density?
I forget which way round it works. So instead of it actually representing density, it represents phase fraction. So right? So if you're blue, you're one fluid. If you are red, you are completely the other fluid. So think oil and water. I forget what the parameters I chose in this case.
It must be denser in the blue.
Right, exactly. Yeah, it has to be denser in the blue. Yeah, you're right. Okay, so yeah, that was just a bit of fun I had at the end. So what have I showed you? I've showed you at the beginning something quite simple. How do you construct geometric integrators for Hamiltonian ODEs, which is kind of neat. And then I went and studied some standard numerical schemes and how well they act on a pendulum and things. and then I went crazy and started showing you phase field problems and how to construct numerical methods that are physically consistent. So they respect the physics that you've inbuilt into your model. And I think this is a good idea. Otherwise, you end up with artifacts. This allows you to remove certain artifacts, and you can generalize it to really very complicated models, which is what I showed you at the end. Okay, so there's a couple of references. So the first part was actually done by an MRes student of mine last year, and then the other two publications are available from there. So thank you very much for listening.
So, questions, comments? Yes.
Well, what happens if you have a completely integrable system? So, for instance, if you have KDB, could you apply your ideas to more conserved quantities?
Very good. Yes, very good. So this is exactly what he's looking at. So this is what my student's looking at now. Yes, so if you have an integrable system, an integrable PDE, so KDB, for example, has the three standard quantities, mass, momentum, and energy. And then you can bootstrap and get infinitely many quantities. Who says that? Muro or something like this. The Muro transform? Yeah. And what we can prove is that you can have the first three, but no more. So in doing things in this fashion allows you to get the first three conserved quantities, mass, momentum, energy, for KDB anyway, but you can't go further, actually. There's a limit. I mean, you're discrete, so you're never going to get all. There's infinitely many, so I can't have all of them. The limitation with this approach is the first three. So you can get the base three, but you can't get further, which I thought was really fun. Yeah, that's just KDB though. I don't know about other integrable systems.
So can you give us any idea as to what the physics is behind these additional fluxes that you have to introduce?
So I would view them more as compatibility conditions rather than physically relevant things. They're compatibility conditions in the numerical scheme that makes them consistent, physically consistent, the scheme itself, if you see what I mean.
If you think of it going in the other direction from the discretized version to the PDE, then those quantities...
Of course, I mean, then they're meaningful. So, okay, fine. Yeah, I understand what you mean. Yeah. Did I ever write the fluxes down anywhere? It's very hard to tell you what physically a flux means without a flux. There's one. So I mean, in the continuum limit, these things go away.
Yeah, but that's exactly the question. What do they
Right.
represent in the discretized version?
It's
Well,
a
that's
it's a
okay.
very good question. I don't know the answer. I'm not the physical modeler. So
Okay, I have another one.
Go on.
Usually when you have an interface problem such as you worked on, you have an energy associated with the interface itself. That's gone in your scheme.
Right.
How would you handle that?
Oh God, you ask hard questions.
Well, the easy ones are no fun.
This is true. So how would I handle an additional energy functional that?
Yeah, suppose you had an excess energy at the interface, which you typically have.
That's another very good question. I'm not sure.
Okay.
Something to think about, certainly. Wow, you guys are full of really hard questions. Okay. Maybe. I wouldn't like to say yes because without doing the computations, I'm not sure. But maybe.
Yeah,
Maybe.
because the velocity oscillations are caused by the sharp gradient.
Right. It's yeah. I mean, it's the advection dominated stuff, right? So DG tends to be very good at dealing with this kind of thing.
Yes.
Whether or not it would completely remove them, I'm not convinced. I'm not convinced. So for example, when you have a thin interface, do I have a numerical? So say here, when I have a thin interface, why are you not working there? When I have a thin interface, there's a compatibility condition between the minimum mesh size in the interface. There's a minimum mesh size that you have to have in the interface to be able to correctly resolve it. And if you don't correctly resolve it, then your numerical scheme thinks you're in this scenario, and you have very steep gradients, which means you're always going to get this Gibbs phenomena, this oscillatory behavior. I think adaptivity would cure this phenomena, but this in particular would
Yeah.
I don't think this on its own would.
The problem is that we don't want to refine the mesh to be very, very small because it's
Not even locally. You don't want to do it locally either. Why not? Why is this a bad idea?
because it's like the computationally expensive, right? Or to generate the mesh is very complex.
It depends. So I mean, you could use adaptive algorithms based on. So what I showed you right at the beginning with the ODE case, the a posteriori estimates. You can use adaptive algorithms based on these, or just. I mean, if you're interested in this approach, you just need to use a gradient indicator, right? If your gradient is high, you need small mesh size somewhere near it. So I guess you could do something like this, and the generation of the mesh is sort of done in real time as you're simulating.
Yeah.
So I realize practically a lot of people don't like this because it doesn't lend itself well to parallelization, right?
Another question is that why you don't like the artificial dissipation?
Why do I not like it? Because it destroys the physics of the problem. In my humble opinion.
Care more about the physical.
Right. So in this case, I care more about the physical properties. Sort of. I mean, if I just add more dissipation in there, then I'm destroying the dynamics. I can miss a lot of very fine scale features. If I'm looking at I don't know, like a Rayleigh-Taylor instability or something. Yeah, and if I throw a load of numerical diffusion in there, I'm losing a lot of small scale features. So, and you want to pick up as many of those as you can.
Okay, yeah, because now I'm not doing the multi-phase, so just one phase. So that if I add some like artificial dissipation, I can also get the right velocity field and right pressure field.
In one phase, maybe. Yeah, in one phase, maybe.
So I
Maybe.
I didn't think about it. Yeah, but I think this idea was quite interesting.
Thank you.
So, any other questions? If not, let's thank Tristan.
Fine.